I'm going to be talking about autonomous shipping security. I actually really struggled to come up with the kind of direction I thought this talk should take. It's a massive topic. There's so many different areas to shipping security. And when you bring in autonomous ships, it gets even more complex. Just to introduce myself, I work for a company called Pentest Partners. And we're pen testers. So what we do is we go around and we test the security of various systems, banks, mobile apps, financial institutions, insurance companies. But what I do is I deal with the stuff that's not normal computers. So that's the Internet of Things, it's vehicles, and kind of importantly here, it's ships. We've tested a load of ships over the last 6-7 years. Cruise ships, container ships, offshore workboats, quite a range. And I used to work at sea quite a long time ago on container ships. So I'm going to jump right into it. Ships traditionally have had what's called an air gap. The bridge and engine room systems, the control systems or operational technology have had an air gap between them and the kind of more vulnerable systems that are connected to the internet, things like the corporate network on a ship, any third parties that are on board, the crew welfare network, and so on. There's been that gap between all of them. And that means even if you compromise many, many systems on the ship, you still can't get to those control systems. You still can't do anything particularly awful. The thing is when you think about autonomous shipping, you've obviously got to have control of propulsion, steering. You've got to be able to monitor all of these systems. So there's a connection between those vulnerable networks and those control networks. And that's got rid of that air gap. And it can make it really, really hard to secure those systems. So when we think about a normal vessel, this is an oil rig, we look at the bridge. It's fairly typical. I think even on an autonomous ship, you're going to have a bridge of some form, maybe not quite as big, maybe not as plush as it would be on most ships. But that's the thing that controls the propulsion and the steering. And on nearly every large ship nowadays, all of that is networked. All of them are computers driving those screens. They're incredibly complex. Of course, you've got all of the machinery down below as well. I was an engineer, so the machinery is the stuff I understand. Bridge stuff, navigation, I don't really get that, to be honest. Now, I think one of the massive challenges in autonomous shipping is going to be connecting up all of this machinery and monitoring it. I mean, when you went to unmanned machinery space in the evenings on a container ship, it was pretty rare you'd get through a night without an alarm. That's obviously got to be moved forward from so that you can let ships run unattended for long periods of time. But, you know, we're starting small with work boats, security boats, things like that. And then we're going to move up to these bigger cargo vessels. You've also got all of the other networks on the ship. So this is off a workboat. It's a satellite TV system. It's the corporate network. It's the server that does email. It's all of those systems, those normal things, those normal computers you have in any office, in any business. Obviously, they need to be secured as well. Now, when we think about information security, we often use this triad called the CIA Triad. The C stands for confidentiality. So that's the ability to hide information from those unauthorized to see it. And that's often what we think about when we think about our phones, when we think about Facebook and our bank accounts. It's stopping people from seeing what they shouldn't be able to see. It's the thing that most people think about when they think about security. The next one's integrity or authenticity. They couldn't have two A's, so they called it integrity. That's making sure that data is accurate and unchanged, an accurate representation of the original. That's important when you're doing things like instructing your bank to transfer money. They need to make sure that that request is authentic. It's important when you get the position of a ship fed back to an onshore control room that's controlling that ship remotely. You need to make sure that that position is authentic. No one's tampered with it. But probably the most important one when you look at autonomous ships, when you look at shipping in general, is availability. That's the ability to ensure that information systems are readily accessible to those authorized. I mean, just think of the example. If a ship cannot work, if it can't sail, if there's a container ship alongside and it literally can't leave the port, it's become unavailable. that has a massive problem. You know, it's going to cost them huge amounts of money. Equally, if you're looking at a passenger vessel and all of the fire alarm systems stop working, that is an availability issue. So availability actually becomes really important when you talk about real world systems. They've got to work. If I'm remotely controlling that vessel and I can't do that and it goes off on its own back, we've got problems. But that leads to the fourth impact, sorry, which is safety. Really, when you think about any system that can impact either people's lives, you know, the safety of people or the environment, safety has to override all. And when we look at maritime systems, really, safety is the most important thing to consider. Whoops, and I've just gone all the way back to the beginning. Sorry about that. Now, just to discuss some language that we use in information security, we talk about vulnerabilities, and they're weaknesses or gaps in security controls. So say, for example, you set a weak password on your Outlook account. That's a vulnerability. If you leave vulnerable software, something that we can attack and compromise remotely. If you don't have a firewall, these are all vulnerabilities. Threats are something that can cause harm. Now, there's an important distinction here. You've got active threats. You've got hackers. You've got people who are actively going out there to cause harm. But you've also got threats like natural disasters, bits of equipment failing, which can have massive impact on safety systems. A lot of systems on vessels now are redundant to a certain extent. If you look at, say, for example, a cruise ship, it will have two power systems that largely run side by side and mean that that ship can still operate safely if one of them were to fail. You'll have 2 or 3 fire alarm systems so that if one of them fails, you can still operate safely. You've got more lifeboats than you need. So those threats aren't always active, but we call hackers attackers, an active threat, someone who's going out there to attack your systems. And that's really what I'm going to talk about here. Now, for a hacker to actually attack your system, certain things need to align. That attacker has to want to attack your system. They have to have that motivation to actually carry out an attack. If they don't have that motivation, they're simply not going to go and do it. Now, if that system's not vulnerable, if there's no issues, if there's no security holes, that threat, the attacker, can't do anything. So for there to be risk in a system, we need to have the overlap of a threat that exists, those attackers. They must be motivated, they must be capable, they must be adequately funded, they must have access to those systems. But you've also got to have those vulnerabilities, those weak passwords, those systems that connect between high values, risky systems like the engine control systems and the crew Wi-Fi network. Those vulnerabilities have got to exist alongside that threat to produce risk. A simple formula, not really a mathematical formula, but we look at it this way. Risk is the product of a threat, a vulnerability, and also the impact if that vulnerability were exploited. So say, for example, someone guessing a password just means they get access to the steward's email. That might not be the worst thing in the world. They could use that for a phishing attack against other people, but it's pretty low impact in the general scheme of things. If, though, they could steer the ship remotely, if they could discharge the CO2 fire extinguisher system into the engine room when people are there, the impact becomes much larger. So that threat is the who and the why. You've got the vulnerability, the when, where, and what. What are they actually doing? Those two bits we can look at as the likelihood. You've got to have that threat and vulnerability. The higher the vulnerability, the higher the threat, the more likely that something happens. But it's that impact, what actually happens as a result of that. Really importantly, from an attacker's perspective, rather than a defender's perspective, high impact attacks are quite often attacks with high rewards. If they can steal a lot of money from someone, that's a high reward. If they can cause a lot of impact, that means they can carry out ransomware attacks more effectively. Ransomware attacks are incredibly profitable, where they stop lots and lots of machines working. If you take out all of the corporate machines on a container ship or on a cruise ship, it really can't operate effectively. It becomes incredibly difficult. So what are the impacts? Well, you could have remote control of the vessel. That's the one that most people talk about when they think about cyber physical systems. When you talk about car security, when you talk about ship security, people are thinking about actually taking control, being able to steer it, being able to move it. You've also got that denial of service. Coming back to availability, can you stop the ship working? Can you stop components of the ship working that mean it's going to cost that company money? You've got supply chain delays. Nowadays, everything is working in such a just-in-time nature that if we can stop every single container ship for a given line working, that's going to cause serious supply chain problems. Again, that could be a really big impact on the world. We've got environmental impact. Again, if I can cause a fuel spillage, if I can discharge the ballast tanks in the wrong way, we can cause environmental harm. And finally, and possibly most importantly, the biggest impact there is threat to life. You can cause harm to the crew, the passengers, bystanders, even when you've got something the size of a ship being remotely controlled. The thing is, though, to influence the steering or propulsion of a ship, you've got to think about the motivation there. What kind of person would want to do that? Why would they want to do that? The thing is, that's a targeted attack with serious impact, and there's no immediate financial gain. A lot of hackers, especially ones that carry out complex, advanced attacks involving lots of skill, they want money. They want some reward that's tangible. Whilst it might be seen as fun to steer a ship remotely, cause disruption, how many people are actually going to be motivated to do that? How many of them are going to be motivated to actually cause a significant number of people serious harm? Now, I'm not saying you need to ignore things like this. I'm just saying that the number of attackers that may want to carry out these kinds of attacks might be limited. Of course, though, when we look at the media, when we look at films, that's what people go for. Speed 2, Cruise Control, which is maybe not the best film. I'm sure your work in maritime films are just not particularly realistic. But Speed 2, Cruise Control was about taking control of a cruise ship, though the attacker was actually on board at the time. Another film, Hackers, and you might not have seen this one. It's a bit of a classic within the security community. Again, that is about people taking control and capsizing vessels remotely. It might not be the most realistic risk, though. The one that we notice when we're dealing with maritime customers is they're worried about interruption of service. That could be stopping a cruise ship from being able to take orders in the bars, take orders in the restaurants, stop them being able to order new stores, stop them being able to organise shore excursions. But say for a container line, Maersk or so on, if you stop them being able to operate their entire autonomous or normal fleet, they're going to have big problems. They really want to avoid that. And that leads to ransomware. The idea of stopping these systems working and then saying, look, we want money. If you give us money, we'll let you use those systems again. These kind of attacks are incredibly common. And so far to date, they've largely only hit normal machines, corporate machines. The thing is, as networks become more connected, as the bridge, as the engine room become connected to those networks that are connected to the internet, there really is the potential for ransomware to start hitting these control systems, which could have serious impact on safety and stop ships working entirely. So that's all the theory stuff. I want to show you the actual issues we see when we're on ships. So I'm going to go through a series of issues we've seen on oil rigs, workboats, cruise ships, and so on. The first one, and I'm sure if you've ever been on a ship, you'll have noticed that people stick the passwords onto monitors. They put them on keyboards, on the computers themselves. They're absolutely everywhere. Now, the thing is that quite often when you look at the advice, people say, well, you should make the password long and complex and you shouldn't write it down. That might work on my laptop. That might work on my own computer. But when it's ECDIS, when it's a control system on the bridge, when it's the load computer, when it's a safety critical system, we can't go messing about having to unlock that system with a password that we might forget in the heat of the moment. There's often a massive gap between the advice that people give out and what's actually practical and actionable on a ship. The amusing thing was this issue was reported of the password of 1234. We said it should be made a little bit more long and complex. The fix, add a 5 onto the end of it. Not great. But it is endemic. It's absolutely everywhere. We see these passwords written down on nearly every ship we get on board. Now, when you're physically sat at the computer, that might not be so much of a problem. If I have to be on the bridge to use that login to log into that machine, that's not really serious. But we do find that people still set bad passwords and reuse the same passwords across lots of systems. Now, one thing you get on a lot of vessels is something called out-of-band management. And the idea here is if your internet connection goes down, if your VSAT goes so you can't connect to the internet, and that might be by accident, it might be by someone reconfiguring something, you've got this out-of-band management box, which has got its own independent connection and VSAT through to the internet. So you can log into that, and then you can connect to the core network, the VSAT router, bridge systems, engine room systems. And generally that's operating on a very, very low speed satellite connection. As a result, these out-of-band management devices store the passwords for the network, for the satellite router, for bridge systems. They're stored on the box on the vessel itself. You connect to the box then connects out to these other systems. So from my perspective, if I'm on one oil rig out of a fleet of 20 oil rigs, and I can gain access to one of these out-of-band management systems, that means I can attack that single out-of-band management system and get passwords that might work on other oil rigs. And that is exactly what we did. We went into one of the equipment rooms and we pulled out an Uplogix out-of-band management system. It stores its data on a hard drive. We pulled the hard drive out and we read it with our laptops. Now, all of the passwords that it stored for accessing those other bits of equipment were encrypted. The thing was, they were encrypted with the same password on every single one of these boxes. We reverse engineered that. It wasn't particularly difficult. A bit of code, pretty short code, turned that encrypted password that we found there into a plain text password that we could then use. Amusingly, the key that it used was fixed across all of them, but it was Bob the Builder based, so Muck and Dizzy were mentioned. I don't get where that came from. But that gave us a password for the core network on that oil rig. And we found out that those passwords worked across all of the oil rigs in that fleet. So it was a high value password that allowed us to compromise other systems. Luckily, the bridge systems, the VSAT, they all had different passwords. Now you might recognize this. This is the dynamic positioning system on oil workboat. So it's designed to hold the vessel in a fixed position. One of the things we do when we test ships is we quite often go routing about in cabinets, seeing how things are connected. There's quite often a difference between what the designers of the networks and systems intended and what actually gets put in place. So that might be that the people that were on the ship the day this system was installed something slightly different to that was what was expected. It might be that something's been added over the years. Things change. So we look under there and it's running to conventional Windows machines. That's not too much of a problem. We go into the cabinet below. It's got a load of networking equipment connecting out to other systems and power supplies. Nothing too interesting at the moment. But then we look at the top there and there's a modem. The vendor that had installed this dynamic positioning system actually put in remote access. They connected it into the ship's network. Now, it did turn out that it was only really possible for the vendor to remotely access the dynamic positioning system. But if the vendor can access it, if the vendor's compromised, so can an attacker. And this just wasn't known about by the ship owner. The next one we found was a system that I think they thought it had been architected securely, but it hadn't. This is one of, I think, 5 generators on a similar type of vessel. And I've got my laptop connected up into the network in there to examine the traffic and see what's going on. Thing was, I didn't really need to get that technical at this stage. I just needed to open my eyes and have a look. So in that cabinet, we've got some circuit breakers. We've got the diagnostics connectors for the CAT engines. And we've got that little box on the top right there, the MB Spider, which looks a bit like a router. So we thought we'd have a look at that a bit more closely. Now, it does have an antenna on it, and it can actually connect to cellular networks. I mean, realistically, this is, down on the bottom plates, you are not going to get a connection. So that's not an issue. So we looked at the manual of this device. And we noticed, interestingly, at the bottom there, your router at home will have a WAN connection, the one that goes out to the wide area network, the internet. That one will be heavily secured. Then you'll have your LAN, your local area connection. That will be the less secure network, the one that you can access the administration interface, the one that you can change settings and so on. But on this one, it says LAN/WAN. Surely it's 2 ports. You look on the bottom though, and it's not, it's a single network port. Now, the intent was this was acting as a firewall. Traffic would go in that port, it would be firewalled, and then it would come out of that port. The problem is that lack of physical network segregation means that we can do bad things. So when we looked at it as a system, we had the technical VLAN. So that's a network on the ship that's designed for more sensitive control systems than the corporate network. We had our little MB Spider router on the left-hand side, and then that went out to a series of switches by each engine with a controller and a power monitor. They were then connected through to the generators. The intent was if you wanted to remotely access anything, you'd come in from that tech VLAN on 192.168.1.0, connect to the router, and at that point, you'd be granted access to the other network to do things. But we don't obey the rules. We're hackers, we're attackers. We don't have to do what's intended. So we came along, and instead of having our IP address set to 192.168, we just set our IP address to be the same as the generator controls. That MB Spider, that firewall, was no longer a problem for us. We just came straight in and we could compromise the controllers on the generators, and we could cause impact. We could open the breakers on these generators. So when you looked at it, this was on the breaker panel. You had these deep protection and power management, PPMs. These were the things we were connecting to. Now, of course, interacting with one of those, it doesn't just have a web interface with open and closed circuit breaker, but they have a freely available tool. I just typed in the IP address of one of those controllers, and then I had live readings on my laptop, and I could control things. I could change parameters. I could even reprogram how that operates. That could potentially take that generator out of action until someone reconfigured this piece of equipment. So the implementation there, it looked like they tried to do things securely, but through an omission, it meant that we could access them. I did this from my cabin. It was possible to get onto the tech VLAN from the cabin using the televisions, which had a network connection, so you could stream and watch video. Now, the next one is about efficiency. Efficiency on ships is really important, especially when it comes to fuel efficiency. And quite a few companies install remote monitoring systems. See, the idea of these is they gather data, particularly from the bridge and engine room, things like RPM, speed, so you can calculate slip, things like that. They gather those data, they pass it through to the main network, and then they send it through to the internet. Now, again, this was a case of someone knowing the system was on the ship, but they didn't really understand how it worked. So we couldn't actually physically find where this remote monitoring was being carried out from. We knew the company could see the data. We knew the data was on the bridge. So we had to hunt it out. And it took us a fair while. So the box at the top there is the Voyage data recorder. Now, the Voyage data recorder takes all of that data, generally on serial lines, into it, and it stores it on hard drives, solid state drives. It seems like a sensible place where you'd also put a box that monitors that data. But there wasn't an obvious cabinet. There wasn't anything there that looked like it should be doing that, except for that panel halfway up. It was actually screwed shut into the bulkhead. So we unscrewed that, and there's a pile of network equipment. Now, that box on the right-hand side was the thing that was gathering all of that serial data up and then spitting it out to the network so it could be monitored remotely. Now, we wanted to work out, could this impact the vessel? What could we do from that perspective? It's a really interesting box. If it's connected to all of these serial networks, there's potential for us to put data back onto that serial network. That means we can do things like inject values. we could cause a storm of traffic on that network that stops other devices from being able to read the genuine values. The thing was, in this case, and this is why it was important for us to physically locate it, they'd done something very clever. These serial lines have got a ground, a receive, and a transmit. Now, for each one of those serial lines coming in here, it only had 2 wires, ground and receive. There wasn't a transmit wire there. They'd only connected half of the serial line. That meant it didn't matter what I did to that box to compromise it. There was simply no way for me to inject traffic onto that network. So often it's really important for us to understand how these links are actually built up. If that transmit wire had been there, that would have been a much, much higher risk. If we'd been able to put data back onto the bridge from that converter from serial through to IP, we could have caused bad things to happen. As it was, all we could do was impact the monitoring. Another one we see all of the time, and I think this is going to start becoming a big, big problem with autonomous ships, is what we call shadow IT. So this is when people start putting bodges in, putting things in to make their lives easier that perhaps you don't know about. Perhaps the designer, operator of the vessel has no idea they exist. Now this is, as you can see, it's a commodity, a home router, Wi-Fi router. We found this on a walk-to-work crane on a workboat, connected up, so it could be controlled from a laptop. The password for that Wi-Fi router was predictably poor. So someone, again, within proximity to the device, would be able to control that network, control that crane. Not great, but no one really knew about this. It certainly wasn't on any inventory or plans that we had seen. The next one, this is on an oil rig. We found that we could see a Wi-Fi network in what was called the oily zone, so the hydraulic workshop. And it turned out that someone had just installed their own Wi-Fi router onto the corporate network so they could use laptops in that workshop. The thing was, we could access everything from that perspective. It made it incredibly vulnerable. Again, you had to be on the vessel at this point, but it's still quite a serious erosion of control, of security controls. Imagine if this was a container vessel and you could come alongside and connect to one of these networks and do as you please. So dodgy Wi-Fi being connected up to the corporate network, we've found that so many times now. Sometimes it's just to make people's lives easier. Sometimes it's so they can watch YouTube instead of work. Lots of motivations. I do think that might be one advantage of autonomy, is that you get rid of some of these aspects. You don't have to have as many corporate machines on the vessel. The crew network, the welfare network doesn't have to exist. Some of the things I've seen on welfare systems, yeah, don't want to go there. Not in a professional setting anyway. Another thing we've noticed is quite a few people aren't really realistic about the risks. Now, this was a comment on a blog post that we made, saying that someone had not ever, well, over the past 6 to 8 years, had never seen an exposed USB port on an ECDIS computer. Yet there's me, after being on lots and lots of different vessels, and I actually don't recall seeing an ECDIS system that doesn't have a USB port. Some of them will have a little lock put in them, but most of them don't. Lots of them, people just use a normal USB key to perform updates. I mean, as soon as that was said, I went and found the last time I took a picture of an ECDIS keyboard. Now, I'm no expert, but that on the top right-hand side of that looks an awful lot like a USB socket to me. Another thing we often hear is that old, out-of-date systems don't exist on ships anymore. Everything's getting updated. This is the radar and ECDIS on another vessel, Windows XP. It's as up-to-date as the vendor will provide. It works. In this case, those systems are air-gapped. They're not connected to a network, which means that it's hard to exploit those vulnerabilities. But they exist. I think even on new vessels, we've tested a couple of new cruise ships within the last couple of years because they've not been doing as much as they normally do. And yeah, we're finding XP on those. So it's almost an endemic problem. Some of you might recognize this software. This is off the load computer on a ship. So it's designed to take the loading, ballast tanks, fuel tanks, cargo, passengers, and so on, and calculate if the ship's stable or not, and what you need to do to keep it stable. Again, I'd like to point out, I'm not a decky, I'm an engineer. This kind of stuff's black magic. But this is a critical system on nearly every vessel. It's also connected to critical systems. Now, on most vessels, you have what's called an ICMS or an IACMS, which is an integrated control and monitoring system. So that's the screens, the keyboards, the mice that you use to interact with the machinery. The bridge will often have one perspective onto it, the engine room another. But you can open and close valves, start and stop motors, mess about with the engines. There's an awful lot you can do through these systems. But you also need to get data from those systems through to other places. Now, the load computer needs to know things like, what are the levels in the ballast tanks? What are the levels in the fuel tanks? How many passengers have we got on board, and so on. Now, when you're integrating that load computer into a new vessel, you've got to work out where to get those signals from. And quite often the easiest place is off those serial lines that carry that data. Now, what we found was there was an air gap between the bridge and engine room systems, the ICMS systems, and the rest of the vessel. So on the left-hand side, you've got a really complicated network that's kind of normal on a cruise ship. Now, those bridge systems have got the IP connected devices, the network connected devices. And to interact with serial devices, things like tank gauges, strain monitors, you have what are called IP to serial converters. They're incredibly common. I don't think there's a single modern ship that doesn't have one of these on board. Moxer are an incredibly common brand. So it takes serial in one side, it reads those values and spits them out the other. You can connect to the network in the other direction and cause it to spit serial signals out. Now, when the load computer comes along, they want to be able to read all of those serial signals. So they get their own IP to serial converter and they connect it up to a computer server that sits in a room somewhere where it's convenient to gain access to those systems. That will probably be somewhere, maybe not on the same deck as the bridge. It won't be a convenient location. So you've got a user interface for the load computer, a normal desktop computer that will normally sit on the bridge or in an office near the bridge. They've obviously got to be connected to each other to get those readings through using a network connection. Now, what we found is that often people don't want to run network cables long distances on ships. It's awkward. You can't just run it under a door. You can't just drill a hole in a deck or a bulkhead to get it through. You know, it can be hours of work to open up a deck penetration, put a new cable in and run it. So people go for the low effort route. Now, what had happened is when the load computer UI and server had been installed, someone had just plugged them into the nearest network socket that anyone could see. So they're just going, oh, there's a network socket, I'll plug it in. So the situation was these were just plugged into random network sockets as near as possible. But the thing was the engineers who installed it found that the system worked. They plugged it into two network sockets, quite physically distanced from each other, and the two computers could speak to each other. So it worked. Everything worked. They didn't have to go and run a cable. They didn't have to make any changes. So that's what they decided to leave in place. So why was that the case? Well, on this particular ship, if you connected to a wall port and you didn't have what was called an 8021X certificate, a certificate on your laptop that allows you to authenticate to the network to say, I'm meant to be here, you got put into what's called the tar pit. That was a little closed network where everybody who shouldn't be there was put in it. Those two computers, the load computer UI and the server, didn't have this certificate. They were put into the tar pit. But a side effect of that was any two computers in the tar pit could speak with each other. Now, of course, a cruise ship's huge, absolutely massive, and there's network sockets everywhere. What we actually found was we could be sat in the bar or by the pool, find a network socket, plug into it with our laptops, and we also got put into that tar pit. At that point, I could connect through to the load computer server. So I had network access through to that. The thing is, and I'm not going to name the brand here, but it's the big one that's used on many, many ships. The default username and the default password are both variations on the company name. They're known across the industry. The same ones used to log into that user interface on the bridge are the ones that are used to log into the server. Everyone knows the one to log into the bridge because when the machine loses power, which again ships do, people have to log into it. So we had that username and password. We could compromise the load computer server. There is no security on these IP to serial converters, at which point we could inject random serial traffic onto that connection. That caused a conflict with the readings that were coming for the ballast tank, the fuel tanks, and the hull stress monitors. So we impacted those readings on that serial line. The thing was the bridge systems then consumed that. The engine room systems also consumed that data. Now, we didn't really get it to do anything particularly meaningful. We just managed to stop it working. But when you're on the bridge of a ship, there's a lot of things you need to take in. If suddenly you can't trust your systems, if they're giving you garbage data, how do you know exactly which ones you can't trust anymore? Causing that kind of like mental overload, especially like if you're coming through busy shipping lanes or alongside, could be a serious issue. The next one is an oil rig. The oil rigs are great fun. They're just incredibly complex and they've generally been modified a lot over time. Generally, they're split into an accommodation and the rest of the network, the rest of the vessel. So you've got the actual drilling systems, you've got the power, you've got the engines, propulsion, and so on. The accommodation's nice and warm, it's relatively quiet. They try to keep it away from the noisy stuff. And people don't generally want to leave the accommodation if they don't have to. The other thing is that when you go out onto the drilling floor, you need to get geared up in PPE, hard hat, boiler suit, you need to check in and out, get a radio. It's a pain. So what networks did we see on the oil rig? Well, its propulsion was completely air-gapped. We found no way of gaining access to that remotely, so that was safe. But again, it had that VSAT connection to provide internet. We had the core network, all of the networking gear, distributing that across the vessel. We had the corporate, the normal machines. We had lots of third parties. You had like subsea exploration, labs and so on. And then you had the welfare network for the crew. But crucially, you had something called the DCN, the Drilling Control Network. And this was a massive system that controlled the drill, controlled the derrick, it controlled all of those systems. Now, it had a remote access feature that the vendor had provided, and we had a really, really good look at that. And it was designed and implemented incredibly well, very, very secure. So we were pretty happy with that. But underneath where the guys who actually control the drills are, there was an equipment room. And in that equipment room, we found this PC, fairly standard PC. And it was fairly easy to guess the password to log into this one. Once we were logged into it, what we noticed was that it had multiple network connections. It had a main, a LAN B and a LAN C. We're fairly sure this is taken off a Kongsberg system at some point and repurposed. Interestingly, if you look at X LAN B there, it's got an IP address. It's already connected to a network. X LAN C says media disconnected. And where it says connection specific DNS suffix, it's blank. Main LAN though says media disconnected. But for connection specific DNS suffix, it says corp.local. That was the name of the Windows domain. It's a very common name for a Windows domain. Now, the thing is, you only get that DNS suffix when you've previously connected that network to something. So we thought, hang on, this looks like someone's disconnected a network. That corp.local was shouting to me, something weird's going on here. So I looked at the wall to my left. And what did I see? Well, there was another network connection, which was very, very close to a network socket on the wall. Now, everyone knew we were coming. They knew the pen testers were here to test the security of that ship. So I thought, someone's unplugged this. What happens if we plug it back in? So I plugged it back in. I was given an IP address in the corporate network. So it's fairly likely that that's the case. We've now got a bridge between the drilling control network and the corporate network. Now, it's our suspicion, no one would confirm this, that people didn't want to get all geared up and walk out across the rig to go and make small changes to the drilling control network. So what they did was they put in this computer, what we call a jump box, to allow them to access the drilling control network from the accommodation. It makes sense. We see this done a lot in industry. We see people circumventing security controls because things are awkward. They've got in the way of people doing their jobs quickly and efficiently, and security can often suffer. Now, that might not be too bad. The corporate network, again, that should be relatively secure. The problem was it was running TeamViewer as well. It was literally running free TeamViewer, which was connecting to the internet. The ID and password, the ID was hard to guess. The ID is a 9-digit number. The password, let's just say again, it was pretty easy to guess. I gave my colleague who was at home a call and I said, can you connect? And he could. The situation now is we've got people on the internet able to access the drilling control network. Not a great situation at all. Another one are forgotten systems. This one was found on a container ship. There was this weird kind of unmarked box. No one knew what it did, so we thought we'd dig into it a bit more. Now, what it had on the side of it here was a converter between RS485 and RS232, so between two different types of serial. So we're thinking it's monitoring something probably to do with control. We had a bit of a dig about, and it turned out there was a screen on the bridge that was connected to this system, but the system was no longer used, so someone had stuck a checklist over the screen. But we traced out the network. It was one of these monitoring systems that was designed to take readings from the bridge and engine room and send them through for looking at through a web interface. It's called Blue Tracker. It had two of these IP to serial converters, one of them connected through to the bridge systems and one going down through to the engine room. So we didn't know what kind of data and how they were connected. So we had a dig about. After a good few hours with a cable tracer, we found the one going to the bridge systems, and it was just that single wire again. It was just data being transmitted from this box on the bridge down to that system. There wasn't the potential for me to inject anything onto that network. So that transmit only works. We don't need to be able to send data back down to the bridge to be able to get the data back. It was NMEA, actually. I think it was speed, position, and things like that. So you got GPS data being sent as a broadcast serial. So we can cut one of those wires, which provides a physical gap that stops us compromising it. So we moved on to the other half of it, the one going down to the main engine. Again, this took an awful lot of cable tracing. It's not easy. We were talking like 9 odd decks, I think, difference, completely undocumented as well. Now, the thing was, this wasn't using something that worked in that broadcast manner like NMEA. It was using what's called Modbus. What we did was we connected to that network to see what data was going backwards and forwards. And the thing with Modbus is it can't just broadcast that data. The server needs to go through to that system and say, hi, can I get these registers? Can I get these coils? Can I read this data? And then the other end will give it back. So it's kind of a bi-directional protocol in that sense. You have to ask the other end for data before it will send it back. So in this situation, you can't cut one of those wires. You need both of those wires available to interact with that PLC, that control system on the side of the main engine. Now, the thing was that unfortunately, we weren't given permission to actually interact with that system. We only had a very, very limited amount of time in port, and then we were underway again. So yeah, messing about with the main engine on a container ship when you're moving, I mean, I think it'd be quite expensive if you broke one of them. So yeah, we weren't allowed to inject any traffic, but we demonstrated that there was the potential for traffic to go down that direction. Now, with a little bit of effort, we managed to compromise that Windows server, that Blue Tracker server. And once again, what did we find? It had TeamViewer running on it. So that was a means of gaining access from the internet through to that blue tracker system, being able to inject traffic via that IP to serial converter that could impact the main engine. The thing was, no one was paying for this system anymore. They decided that that data wasn't valuable to them. The system didn't really work for them. So it had a remote TeamViewer connection connected to the internet, exposing that ship to risk that simply didn't need to be there. So you can see from all these issues I've gone through, some of them were introduced at the point that the system was designed. When you look at that little yellow router on the sides of the engines, you could just bypass the firewall on that. Some of them have happened because people want to make their lives easier. Some of the systems have been installed and people have forgotten about them. It's just incredibly easy to introduce these problems onto a ship. And as things become more and more autonomous, as various devices and systems on the ship become more connected, this is going to become a bigger and bigger problem. So what conclusions can you take away from this? Well, availability and safety can trump other risks. It is so important that things like safety systems on the bridge are always available to everybody without having to log in with a complex password. That will quite often mean that security suffers. And to be honest, the security industry is not good at giving practical solutions to these problems. Operational technology, OT, the control systems are complex and different. There's lots of subtleties. There's lots of things that are different to conventional IT systems. The idea of serial protocols, things that essentially have no inherent security, they're very different. And a lot of information security people don't really understand that. So there are differences, and securing OT systems can be very difficult. Air gaps, the idea of keeping these OT systems completely isolated from they're becoming rare. We've seen what are called converged systems on some ships, where all of the control stuff, all of the CCTV, all of the passenger Wi-Fi, all of the VoIP phones are all connected on the same physical networks. They're logically isolated, but if we can break through some security controls, we can do some fairly serious things. You should design security into your systems from the outset. We've come across lots of problems where we've discovered vulnerabilities in systems, and then our client will turn around to the people who built and implemented those systems and said, they're not very secure. And they go, well, you didn't ask us to do it very securely. You have to be explicit here. You have to make sure that you specify security right from the outset. Again, this is one of these areas where I think it's really challenging. The process of shipbuilding has just got, I mean, we were in the yard watching a cruise ship being built. There must have been 30 different significant entities involved in getting the control systems working. I just have no idea how you get them all to design security into systems. The thing is, though, even if you design things to be secure, expect the worst. Expect people to put in a network cable where they shouldn't. Expect people to put in a jump box where they shouldn't. Expect things not to be implemented quite as you intended. Again, this is absolutely key. Security isn't just a point in time. If I get onto a ship and I do a pen test of it, I might say, yeah, things aren't too bad today. No one's going to be able to do anything that bad. But what happens in 3 weeks' time, 3 months' time, 3 years' time, and that ship gets a bit older, when software gets out of date, when new things are implemented? It's a process, not a snapshot in time. So again, that has to be built into the systems. You need to watch your third parties carefully. I think nearly every vessel we've been on has had a significant risk introduced because of something a third party's done. One cruise ship, all of the networking equipment had a 3-character password set on it because a third party hadn't changed the passwords. You get these weird boxes installed. You get people putting cables in that you wouldn't expect. Again, keeping an eye on them, making sure they don't do anything unexpected can be really difficult. And I wish I had a solution to that. It takes someone a little bit different to get a cable tracer, find an unknown box in a rack in a server room and trace out those cables to work out what they've done. Process might be able to solve it, documenting things. One of the absolutely crucial things is applying what we call defense in depth. This is a term that comes from military strategy, which is the idea that You shouldn't just have to break through one control to impact a system. A great analogy is the Swiss cheese analogy, which has quite often been used with COVID. The idea here is that the holes don't align on all the slices of cheese. So although an attack might get through one layer of security, it will hit another layer and be blocked. Now, some attacks will still succeed. They might get through those holes when they align, but you've reduced the number of attacks that succeed. You don't have to be perfect in defense. If you can stop most attackers, you're winning. If that person who does get through gets caught, then there might not be a problem. This leads on to another thing that we found that the maritime industry is particularly weak on. And for some of those reasons, I think perhaps things are a bit out of date and a few years behind. Other reasons are that ships aren't particularly well connected still. You might have the internet on VSAT, but it's slow. It's called Predict, Prevent, Detect, Respond, PPDR. The UK government promotes this in all connected systems. The idea is you predict first off. You understand your risk, you know your attack surface, and you uncover weak spots. So that's more broadly something we call threat modeling. That's working out that someone's much more likely wanting to ransomware your systems than they are steer them remotely. That's working out that your captain probably is more likely to set a good password than a temporary member of crew. You've got to look at these things and predict what the risks are, what the impacts are, work out where you need to direct your focus. The next one's preventing it from happening. And that one's pretty obvious. That's making sure you do change your passwords, minimizing the attack surface, which is just reducing the number of ways into the system, preventing those incidents from actually happening. Most people do some prevention. They maybe didn't do very much prediction, but they've done some prevention. Detect. And this is where Maritime so often falls down. And that's often because there's no one on board who is an IT security specialist. There's no training given at nautical college to tell people how to do information security. I'm sure it's come on a little bit since I'd learned how to use Word and Excel, and that was it. But at the same time, there aren't specialists. That means all of that data, logging, people doing bad things, intrusion detection, your antivirus system sending alerts, they have to go ashore. And that's difficult when you've only got a limited satellite connection. So that detection bit is quite often completely absent. And finally, you've got respond, actually taking action when you detect something happening. That's having playbooks. So you know that if something bad happens, you can unplug that network cable and still keep operating. That's knowing who to call when things go wrong. That's knowing when to get professionals in to help you limit the damage. And then it all feeds back in. If you are breached, then something went wrong with your threat modeling and your prevention, your predict and prevent. So it all circles round. And it links quite closely back to defense in depth. Now, all of this stuff I've talked about, they were what we call pen tests. They're generally days, significant effort and significant cost. And it can be difficult to carry out these tests, especially when ships are underway. A multifaceted approach to security is key. And one of the things that is very recently happened that RENA is part of is something called the Maritime Cyber Baseline. It's a scheme operated by an entity called IASME, who already do this in conventional business, but they've created a standard, a way that you can get on board a ship and check that people are carrying out these basic security efforts, that they're doing those basics right, that the ship is at least secure from most threats. Realistically, a lot of what I've talked about here, the average person is not going to find these issues. They're not going to be able to carry out these attacks. A conventional ransomware operator, the Maritime Cyber Baseline will prevent things like that from impacting you or impacting you as badly. So we're actually doing this training this week on how to carry out these Maritime Cyber Baselines. So again, I think it's a really interesting step forwards. It's just one facet, the starting to getting systems secure.